So the theme tonight is practical. The last talk was actually practical. This talk is going to be like what counts for practical if you have a PhD in type theory. So not very practical. Okay, like you've been warned. There are no inference rules. I took them out. I don't know if that was a win or not. We'll find out together. Okay, so I want to talk about dependent types. Actually, before I even get started, I want to say I'm going to talk about research, and that research was done with many other people, and I want to acknowledge them up front. So Stephanie Weyrich was my advisor while I was doing my PhD at UPenn. She's awesome. I also worked with this guy, Wilhelm Schoberg, who was doing his PhD at the same time, and he's also awesome. He's now doing a postdoc at Yale. I'm going to talk about a language that we developed as part of a larger project that was called Trellys, and that project also involved two other institutions. A guy named Aaron Stump at the University of Iowa and his students and postdocs, and a guy named Tim Sherd at Portland State University and his students and postdocs. Disclaimer, a lot of what I'm going to talk about today is opinion and not sort of fact, so you may agree with it, you may disagree with it. We all have different opinions in this project, so anything smart that I say you can assume is from them, and anything dumb, it's my fault. So let's go on that basis. Okay. So why do I want to talk about dependent types? Well, dependent types have been around for a long time, right? So like a really long time, actually. So, right, Martin Law first wrote about dependent types in the 70s, in the early 70s, actually. So dependent types are old. They've been around forever. And also, I hope I don't actually have to work too hard in this crowd to convince you that dependent types are awesome, right? Like, we've done all kinds of really cool things with dependent types. Let's walk through some examples of really cool things that we've done with dependent types quickly. The standout example is CompCert, right? CompCert's this C compiler that's completely verified. By that I mean there's a mathematical guarantee that the C program you put in has the same behavior as the assembly program that comes out. That's crazy. It's madness. And it's super cool, and it's like a real example of the cool stuff we can do with this. People have done other really cool practical things with dependent types. We've seen libraries for security typing. So these are libraries where if you program using this dependently typed library and your program type checks, you're guaranteed that it preserves the information flow and access control properties that you wanted. Edwin Brady in his language Idris has done really cool work on concurrency. So if you use his concurrency library and your program type checks, it's guaranteed to be free from deadlock and race conditions, which is amazing. So these three examples are all examples where we're using dependent types to help us write programs that are more correct, right? So we're sort of rejecting more bad programs, but that's not the only thing dependent types can do. Dependent types can also let us accept more correct programs. So a great example of that is generic programming. So by generic programming, I mean this idea that we want to write map once and have it work on every data type, or have write functions once and have them work on a wide variety of data types. So you can sort of do this in Haskell if you use these external tools like generic Haskell. But in a dependently typed language, we can actually do them directly right in the language without needing external tools. The extra expressive power of the type system lets us type more correct programs in addition to rejecting more bad programs. Okay, so that was sort of whirlwinds. I'm betting that I don't have to work too hard to convince you guys. By the way, I should have said at the beginning, I'm going to assume sort of a basic understanding of what dependent types are in this talk. I bet that's not true for everybody, for which I apologize, but I have to start somewhere. If there are particular questions along the way, please yell at me, and I will slow down and go back. Okay. So dependent types have been around forever, and they're awesome, but they're really not used for anything. So I consider myself an advocate for dependently typed programming, and still, if I want to write a piece of software, I always do it in Haskell. And to be honest, 99% of the time, I don't even use the really fancy bits of Haskell's type system, right? There's no lifted types in my code almost ever. So I find that really disappointing, right? This awesome idea has been around forever. We can use it to do really cool things, and yet we don't actually do so, even those of us who are really plugged into the community. So I want to say there's a whole, just a giant number of reasons for this, and I cannot even begin to talk about them all, but I want to talk about two of them in particular, two problems that exist in dependently typed languages today, and those problems are the problems of termination and equality reasoning. So maybe you don't know what those problems are, that's okay. Most of today's talk is going to be explaining what those problems are, and then I'll have a little bit about how we worked on them in one research context. Okay, so to spell that out a little bit more, in today's talk, I'm going to introduce a programming language called Zombie. Zombie is a research language with dependent types. It is not like a real language. You should not be looking to write your code in it tomorrow. It's the sort of thing that we developed so that we could explore some ideas, a particular point in the design space of dependently typed languages. So I'm going to introduce the basic idea of Zombie, just sort of give you a taste of it, by way of explaining how we attempted to solve the problems on the previous slide. So in particular, we'll take a look at those. I'll explain them sort of a little bit historically and why I think they're such big problems for writing real software with dependent types. And then I'll give you a flavor of how Zombie does it differently than existing solutions. I'll also, if there's time at the end, say a little bit about Zombie's meta-theory, which will be when we go from pretending to be practical to not even faking it anymore. OK. So that's the plan. Problem one was termination. So I want to explain to you what I mean by this being a problem for dependently typed languages. And to do that, I'm actually going to sort of take a step back and just talk generally for a minute about how we write software with dependent types. Okay? So I want to do an example. And with this example, I want to illustrate that there are sort of two different ways to write dependently typed programs. This is what I'm going to call the intrinsic way and the extrinsic way. So as my motivating example, I want you to pretend that I want to write a function called nth prime. And nth prime spec is pretty simple. It takes in a natural number. And let me say up front, you don't have to understand this code. I'm going to walk through the relevant bits of it. Right, nth prime spec. It should take a natural number n and it should return the nth prime number. Okay, that's the spec. And maybe using dependent types, we want to verify that the number nth prime returns is really prime. We want to get a static guarantee that nth prime always returns prime numbers. Okay, so there's two ways to do this. This is what I'm going to call the intrinsic approach, and the intrinsic approach might look something like this. So what I do is I start by defining a new type called prime, and if you don't read Agda, you can take my word for it that what this type is it's a pair of a natural number and a proof that natural number is prime. So if you don't understand how to read this, that's OK. Don't worry about it. Just believe me, that's what it is. It's a pair of a natural number and a proof that number is prime. And then we might give our function nth prime this type, nat arrow prime. And that type is saying, OK, nth prime takes in a natural number and it returns an element of this new type that I just defined. And I'm calling this the intrinsic approach because the type of nth prime itself says I'm guaranteed to always return to you a prime number. I'm going to compute a proof that number is prime. The alternative approach is what I want to call the extrinsic approach, and that would look more like this. In the extrinsic approach, I give nth prime a simple type. I give it the type nat arrow nat. Okay, and then I prove after the fact that the number nth prime returns is guaranteed to be a prime number. Okay, so this is the extrinsic approach because the type of nth prime doesn't give you the guarantee itself. Instead, I use dependent types after the fact to verify that. Okay, so the extrinsic approach is better. That's a controversial statement, but I'm going to stick to it. For writing most real software, the extrinsic approach is just a much better way to go. And let me try to motivate that for you. So why is the extrinsic approach better? The first reason is, actually, when I sit down to write a function, I don't always know which properties I want to verify about it at the time that I write the function, right? So in practice, I might write a function, and then I'm going to go write some code that uses it, and then I might realize, oh, yeah, I should probably check that the function has this property, because I saw how I used the function. I don't know up front all the ways I'm going to use it. So of course, if I'm working intrinsically, then whenever I decide upon a new property that I want to check about the function, I have to go back and change the function itself, because the function's type encodes the properties that I care about it. Whereas I'm working extrinsically, I can prove those new properties after the fact later as separate things. I think the most important point is that if I'm working intrinsically, the properties that I want to prove about a function end up polluting that function's definition. So in the nth prime example, with the intrinsic version, the definition of nth prime itself computes not just the natural number, but also the proof that natural number is prime. And those two things are done at once as part of the definition of nth prime. And I think that really sort of, it might be that the computational behavior of computing this number is quite elegant. Maybe I'm using some sieve algorithm, some classical thing, right? But that's going to get clouded by the fact that along the way I'm computing this proof as part of nth prime's definition. So with the extrinsic way, instead, I can just define the function using whatever obvious algorithm I want, and then after the fact, I worry about how to prove things about it. Yes?
With the intrinsic way, if you wanted to add more proofs, you'd be polluting its type even further.
That's right. That's right. Of course, you can mix them, and in practice, what we really do is use a little bit of both. But for anything even a little bit complicated, you want to go with the extrinsic way. Yes?
So in the extrinsic approach, what prevents you from going lower and lower in the types of functions?
Yeah, why don't I just program dynamically?
With just bits.
Yeah, great question. Nothing in particular prevents you except that we tend to like programming. We found, the case that I'm trying to make is that we found that programming with simple types, or like Haskell-ish types, or maybe more like OCaml, because Haskell is getting pretty complicated these days, is quite easy and introduces a low programmer burden. But programming with, once we start getting, it turns out, to these more complicated types, they introduce quite a high programmer burden. So I think we've decided that simple types, about the level of Haskell or OCaml, is about the right level of complexity to check automatically. And also there's a technical result here, which is that it's type inference for Haskell is decidable. Well, type inference for Haskell 98 is decidable. And turns out you can add almost nothing and maintain that property. So there's actually a really good technical reason to think that this is a good level to be working at. Okay, the last thing is, in practice, not as often as I should, but sometimes I go back and improve code that I've written before. Maybe I found a faster algorithm, or I realized I needed a new piece of functionality. And if I'm programming intrinsically, then when I go to make those changes to my function, I have to update the function's definition and the proofs about it all at the same time. Whereas if I'm programming extrinsically, I can update the function the way I want, and then I can check if my proofs go through or if they need to be modified or whatever. Okay? So for these reasons, I think the extrinsic approach is a big win, and I think that if you wrote a lot of dependently typed code, you would probably agree. Maybe not. And that's great, because in Agda or in Coq or whatever, you can handle any property you want extrinsically. Well, any property except one, and that one property is termination. Okay? So in Agda and Coq, in any standard dependently typed language, when you define a function, you must prove at that time that it terminates, that it is guaranteed to terminate for all inputs. Okay? And this, okay, so first of all, why is this the case? Why do Agda and Coq make you prove every function terminates? The reason is that independently typed languages were really putting this Curry-Howard isomorphism idea to work, right? We think the types in these languages really represent theorems, and we think programs that have those types represent proofs of those theorems. And it turns out that if you let non-termination into your language, it's really easy to write a program that has any type. And therefore, in our logic, like all of a sudden, all the theorems are true, which shouldn't be the case, right? Only half at most half of the theorem should be true, right? So when we allow non-termination, what happens is there's a proof for every theorem, and that means we don't have a very interesting logic, because we can no longer trust the things that we've proved, because all of them are true anyway. Okay? So this is why, for example, Haskell's logic is not a great logic, because with undefined or with just writing a loop, I can write a program of any type. I said not a great logic, but it is a really cool logic. It's just not a consistent logic. So there are really good theoretical reasons to ban termination, but it stinks. So if you try to write any substantial piece of code in a language like Coq or Agda or Idris, what you found is that it's a real pain to sort of shoehorn your algorithms into the type of thing that they can tell terminates. So my favorite example for this is merge sort. Merge sort is a really simple algorithm, right? You start with a list, you split the list in half, you sort the two halves, and you pull them back together. And it turns out this thing where I recurs on the two halves of the list, that's just a little bit too tricky for the standard termination checking that exists in Coq and Agda. They're able to see that, okay, so the idea is when you make a recursive function call, you want to make sure you're not going to keep doing this forever. And the way they check that is to make sure that you only make recursive calls on a subpiece of your input. It might sound like the two halves of a list are not subpieces of the original list, but actually the first half doesn't quite look enough like a subpiece because you've added an extra nil on the end. Sorry, yes, I have a question. I would love to play with Epigram, but to the best of my knowledge, no version has surfaced in about 10 years. Am I wrong?
I haven't actually played with it either. I just saw by the papers.
Yeah, I think they've written a lot of super awesome papers, and I'm going to talk about some of their work later, also on the subject of equality, and I would love to play with it. But I want to make the point that even if you extend this to well-founded recursion in general, which actually exists already as extensions to Coq, you're always going to miss some of the terminating functions. Okay, so that's a bummer, So great. You're right. We can always do better than whatever we're currently seeing as termination checking, but we'll always miss some, right? That's the halting problem. So So merge sort is a real pain, actually, to define in a dependently typed language. So much of a pain that there's a classic research paper on the topic by Connor McBride and friends. And yeah, the way you end up doing it is that, so splitting a list in half is hard, but splitting a tree in half is easier because you can kind of see that a binary tree has two subpieces. So what you do is you push the list into a tree, you sort the tree, you pull the list back out, and that's merge sort. And that's like really unsatisfying to me personally. It does make the termination behavior more obvious, but I've clouded this like really elegant, simple algorithm. And of course, also the same point I was making on the previous slide holds. If I have to reason about termination as part of the function's definition, then when I change the function's definition, I have to reason about termination all again, and that's a pain. Okay, the other thing, and I think this is the most important thing, is sometimes we don't care about termination right away. So sometimes I want to write a program down and I want to check certain properties of it, but maybe those properties aren't, maybe the first thing I care about is not termination. So making me check termination right away can be a real pain. Sometimes we don't care about termination ever, right? We want to write programs like web servers and operating systems and REPLs that are meant to run forever. I really like the example of GHCI because actually these other examples, they run forever, but they're expected to be what's called productive, which is you send them a question and it gives you an answer in a finite time. But in GHCI, that's not even the case because if you ask GHCI to evaluate a loop, the correct behavior is for it to never come back, right? So sometimes we mean to write computations that are genuinely non-terminating. And remember, my whole point at the beginning was that I wanted to make dependent types more widely used. And part of that is making them more accessible to programmers who are already comfortable with other functional languages like Haskell. And it turns out that proving every program terminates as you write them is a big burden for new programmers, right? It's a pretty hard sell if you haven't had to think about termination before. So even though Coq and Agda have a great reason for demanding termination, I think it's one of the biggest problems for the adoption of dependently typed languages. Okay, so I said at the beginning I was going to talk about a language called Zombie. So let me give you a little bit of a flavor about how we handle this problem in Zombie. And now we're really entering like research territory here. Okay, so this is I'm just going to give you a taste. Okay, so in Zombie, what we've done, by contrast to the Coq and Agda approach, is that the language has two fragments. So there's one I'm going to call the programmatic fragment, and the programmatic fragment is a language that looks like it would look. Yes, sorry. Yes.
Oh, I'm sorry.
That's all right.
Quick question before you get into
Yes, please.
So everything you've said so far, it seems like very reasonable to me.
Great.
But I guess I'm just curious, like in the dependently typed research world, are the things you're saying very controversial, or is it?
So the only really controversial thing that I've said was the part about extrinsic programming being better. And the reason that's controversial is because intrinsic programming is way more fun. Like it's really satisfying to give programs these complicated types. But what everybody discovers sooner or later is that it produces sort of unmaintainable software that's really hard to write. And so I think that's a controversial statement, but I'm willing to defend it. I think everybody realizes that non-termination is a problem, and I have some related work slides later. I'm not the first person to tackle this problem or the equality problem, but I don't think the existing solutions do a good enough job, and I'll justify that claim after I explain my solution. So no, it's no surprise to anybody that these are problems. There is debate about what to do about them. Okay, so Zombie has two fragments. There's what I'm going to call the programmatic fragment, and that looks like Haskell plus dependent types. So it's inconsistent as a logic. It looks like Agda would look like if you turned off the termination checker. Okay, and there's the logical fragment, and the logical fragment's more like Coq or Agda as it is today. It demands these intrinsic termination proofs, and as a trade-off, it's consistent as a logic. Now, so the catch here is the really cool part, which is that although the logical fragment demands intrinsic termination, it can reason about stuff in the scary programmatic fragment. Okay, so I can write yes.
So does this mean programs whose types are in set can non-terminate, and programs whose types are in prop have to terminate?
So that's a great question, and the answer is not quite. So other people have explored the idea of using kinds to separate terminating and non-terminating fragments, and I will actually talk about that approach later, but that is not exactly the approach here. These fragments are not distinguished by their kinds. Instead, the type system keeps track of, as an extra data piece, whether a program is in the programmatic or the logical fragment. So if you're familiar with type theory, you can just imagine that I've added an extra thing to my typing judgment. Normally there's like context, term, type, and I've added also fragment as an extra piece of data. So the type system is just going to track. We'll get to examples, and this will make more sense. So, okay, so the point is, the logical fragment can reason about the programmatic fragment. So I can write my programs in this one language and reason about them consistently, even though I'm not always obligated to prove termination. And I want to take a step back here, because so far it sounds like I'm describing two separate languages, which would be no innovation at all, right? It would just be a program logic for a language like Haskell. And that's not really what I've got here. So I've called these things two fragments, but that's a convenient way to talk about it, but it's not quite accurate. Instead, I've got one language, and there's this sub piece of it that I've identified as the logical fragment. Okay, so basically everything that is in the logical fragment is also in the programmatic fragment. Things can move freely in that direction. If I've got a proof, it's a perfectly good program. But there are some constructs like unrestricted recursion that you have to label them as programmatic. You can't also use them in a logical part. So this is really one language. It's just that some parts of it are labeled as safe and some parts of it aren't. Okay, and most constructs can be used in both parts and go back and forth between both parts freely. So I don't have two separate languages here. It's one language with a distinguished safe subset. Okay, I want to do examples. I don't have, well, yeah, it's type theory examples, so they're going to be easy and simple. But I need syntax for examples, so here's what I'll do. When I write a definition, I'll prefix it with log or prog to indicate whether I'm defining that thing in the logical fragment, in which case I'm going to be obligated to prove termination, or the programmatic fragment, in which case I'm not. So first example. So this is a natural number division function, and the details are not so important. You can trust me. It's a really dumb natural number division function. It works almost all the time, but if the divisor is 0, it loops forever. Okay, so that's the behavior of this div as I've written it. It's not the way I would write it, but it makes a good example for my purposes. So because this program sometimes doesn't terminate, I have to label it with prog. I'm not allowed to label it with log. Okay, because it may not terminate on all inputs. So despite that, I can define it perfectly well in my language, and it doesn't mess up the consistency of the language. And I can do things with it. I can define 3 by dividing 6 by 2, or even define an infinite loop, and that's perfectly well allowed. But these things have to be in the programmatic fragment because they use this potentially scary function. Okay, so then the cool part, the selling point here is that I'm allowed to reason about things like div in the safe logical fragment. Okay, so here I've got a proof called div62, and it's a really boring fact. It says that the division of 6 by 2 yields 3. Okay, so div62 equals 3, and this fact, its proof, is in the logical fragment, even though it's a fact about the scary programmatic fragment. Okay, and the actual proof is just what I would call the primitive equality constructor. So if you've programmed Coq or Agda, you've seen this before. This is just telling the type checker, okay, try evaluating these things and see if they're equal, and if so, this type checks, and if not, it doesn't. So this is sort of, it's not surprising looking at this program that it's safe, because its definition is just this REFL thing, which is a constructor. It's already a value. It's completely evaluated. But it's pretty cool because its type mentions a scary programmatic thing, which, yes?
Sorry, it's just, I'm just wondering, what happens if I write, log div60, colon div60 equals whatever? Yeah, what'll happen is use REFL as the proof.
Right, what'll happen is,
another tactic that relies on
yes.
computational evaluation.
So I have a slide about this in a second, but I'll spoil it for you. And what'll happen is the type checker will say something like, "Oh, I tried running that for 10,000 steps and I didn't get anywhere. I don't know what to do." Okay, so
Practical approach?
Yes, it is a practical approach. So okay, I just want to say one more thing about the logical fragment. Yeah, sorry, question. No. Yeah. Okay.
You prove something like proving like div30 because it returned with this termination problem, but if you prove something like for all n div n0, does that return?
So the answer is that we haven't thought too hard about a good way in this language to state the fact that a program actually does loop forever. So you can, there's a way to state a program terminates, but stating the other thing is, we have some thoughts. I don't have a good concrete story for that yet. It's also not super obvious to me that it's a particularly useful thing to want to do.
So a minute ago you said it's very useful to have some programs that don't terminate.
Right, but proving that they don't terminate is like, why would you want to do that, right? So this approach is most useful. So this approach is most useful when you've got a program that you think terminates, but you don't want to stop to prove it, right? So in that case, I think the approach that I've got here is super useful.
Is div30 equals div30 a theorem or not?
It is. Yes, it is. And that is a theorem, and I think the type checker would prove it. I'm certain the type checker would prove it.
So just to derail your talk some more, do you
Please.
have to write map twice?
Sorry?
Do you have to write the function map twice?
That's a great question, and the answer is not exactly. Okay. The answer is that most things can go back and forth between the two fragments freely. And so you don't really have to write map twice, but also the secondary answer is kind of sometimes you do have to write things twice and we don't have a great story about it. So, in practice what happens is you choose a default, and I personally usually choose log as the default fragment, and you don't label anything, and you get a warning if you're not actually in that fragment, okay? And then things that are in log can automatically freely be used by prog. So if you can prove map terminates, there wouldn't be a reason to write it twice, because you would have written in the logical fragment, and you can use it freely in the programmatic fragment.
But what if I want to map a function that's in prog?
Yeah, so that's a good story. Sorry, that's a good question. I have an answer for it that I haven't introduced a syntax for yet, so let's table it for the moment. Okay, so right, I just wanted to point out that the logical fragment, it's a sub piece of the whole language, but it does include quite a bit. So in particular, you can write recursive functions. You just do have to prove that they terminate. Okay, so so this is like, so I should have just gone to the slide when people started asking about the type checking, but I stopped. So you caught me. Type checking is undecidable, sort of in general for this language. So I should say type inference is undecidable. Type checking is decidable because we just add the caveat that we're only going to run your programs n steps unless you tell us to go, 2n or whatever you want. Okay. So annotations are sometimes required. You might have to annotate and say, this one needs to be run for longer than whatever your default runtime is, if you think it's true. And the equality checking will never be complete because, halting problem. Okay, so the other thing I want to mention is that sorry, I can tell that I'm moving my head away from this mic, and it's probably really annoying to listen to, and I'll try to do better. Okay, so, right, annotated programs, okay, I said you might have to add annotations. You might worry, oh, these annotations are going to have a runtime cost, or they're going to make the terms less pretty. And the answer to that is they really don't. And the reason is that before zombie programs are run, they're erased into a core language called theta. And all of the annotations are erased in this process, so there's no types left in the terms when we actually run a program. And also, we erased a theta before comparing terms for equality. So these annotations also don't get in the way of equality checks. Okay, so that was a bit of a technical point. If you haven't done any dependently typed programming, it may not have made a lot of sense. You can just take my word for it that these annotations don't introduce any sort of runtime burden, and they don't get in the way. Yes?
So what does theta look like?
That's a great question. Theta looks like the calculus constructions with some annotations about fragments, if you're familiar with the calculus constructions. The better answer is see my thesis. Which is an unsatisfying answer, or see our Popple 2014 paper. That's a good question. So the answer is it depends on what language I'm really calling theta. So in the implementation of Zombie, yes, it looks like more like ICC star, which is the erased implicit version of the calculus constructions. The language that we prove things about doesn't have the implicit bits because that's a lot of work. Great question. Okay. Next, explicit logicality. So in a minute we can get back to the question about map. One cool thing is that we've given in this language a way for the fragments to explicitly talk about each other. So you can have a type, like here I've said foo has the type A at P. And what that means is foo has the type A in the programmatic fragment, regardless of what fragment I'm currently working in, right? This is a way for each fragment to talk about what can be type checked in the other fragment. So also this slide is going to be abstract. I'm going to get to an example in a second, I promise. So here's the intuition, which may help or may not. If I'm in fragment 1 and I am type checking a term foo and it has type A at fragment 2, what that means is that fragment 1 can safely observe that foo has the type A in fragment 2. Okay, I don't know if that helps or not. We'll find out. Here's a really simple example. In the programmatic fragment, I can observe that 1 plus 2 equals 3 in the logical fragment. Okay, so there's something subtle and really cool going on here that I'll get to in a second. But yeah, the programmatic fragment can observe that REFL is a good proof of this fact, even though it's the programmatic fragment. Okay, so why is this useful or interesting? Here's an example. Imagine I'm writing a SAT solver. I might give a SAT solver a type like this. It takes in a formula f, and it tries to produce a proof that f is satisfiable. Okay, just pretend that's the type makes sense, or maybe it does. And the thing about this is SAT solvers are complicated programs, or at least good ones are, and so I may not want to prove up front that the SAT solver terminates. In fact, I may not actually care if the SAT solver terminates. The thing that I really care about is that if the SAT solver says the formula is satisfiable, it really is, right? Because in practice, I might give it a formula that takes till the end of the universe anyway. So the property that I actually care about is if you tell me it's satisfiable, it really is. So using this at type, I can express that property, and here's what it would look like. What I've done is I've added an at L at the end of this type. And what this says now is that the SAT solver, here, let me walk you through it a little bit. So solver is still in the programmatic fragment, so solver may not terminate. But if solver does terminate, we're guaranteed that the result type checks in the logical fragment. That is, that the result is good as a proof. So solver is kind of a partial decision procedure. It's not guaranteed to terminate, but if it does, I'm guaranteed to get a proof out. And that's really cool. You really cannot express this kind of thing in an existing language like Hawk or Agda, at least not easily. Yes?
This seems like it would involve some reasoning about strictness and laziness.
So Zombie is a strict language. Everything is strictly evaluated. And things go quite wrong if you try to do it in lazy ways for interesting technical reasons that are in my thesis and in our POPL paper. One thing you can do, although we didn't because we thought it made the language more confusing, is make programmatic things evaluated strictly and logical things evaluated lazily, which is actually a research avenue explored by Aaron Stump as part of the broader Trellys project. So Zombie is strict. You're right that this is intimately tied into the details of why it works.
Why does the at only go around the stat and not around the entire page?
I could have done it either way. Would have meant basically the same thing, I think. There's no good reason. So putting the at around the maybe isn't very interesting, because if I get nothing out, well, okay, I have nothing, but there's no content in there. It doesn't matter that nothing type checks logically, right? What I care about is if I get the proof, I want that proof to type check logically, which would have been implied by putting it on the outside, but I don't think I gained anything. I used to have it ambiguous on the slide, and then I got yelled at about 10 times, and so I did it this way.
So that's a nice type.
Thanks.
But I guess how does that affect how you can implement solver? Maybe.
Yeah, it means that in solver somewhere you're going to have you're going to produce actual proofs, right, somewhere deep in the bowels, and the type checker, when you get to those parts, is going to check that those type check in the logical fragment. So you can sort of imagine that the type checker, as it descends through terms, it's usually deciding to check those terms at the same fragment I'm currently in. But if it encounters an at L in the type it's checking it at, it's going to switch and now start checking it using the rules from the other fragment. I don't know if that was a helpful answer. So to answer your question, I might have to define two maps, not one in the logical fragment and one in the programmatic fragment, but one which takes a function which takes f whose type is a arrow b at p, and one who takes a arrow b at L. Okay, I might have to write those two separate maps. So we would like to have something like effect polymorphism, but there's too much to do it all at once, so we don't have that story yet. I don't think it's hard, and in fact, my colleague Wilhelm in his thesis got a little bit closer to being able to do that. So I think it's quite close. Yes.
So I'm a little confused how the keyword before the name and the at things work together. Can you imagine this being equivalent to having a at R around the entire thing when you write the proxy for it?
What's at R? You mean at P? Yes, except if I'm working in the logical fragment, there's some restrictions, great question, about the so I was going to skip this slide because it's a little bit technical. So the programmatic fragment can make any observation about any fragment using an at type. In a logical fragment, I have to be a little bit careful. If I'm making observations about programmatic terms, I run the risks of introducing non-termination into the logical fragment. So in practice, if I'm working in log and I want to add an @p, the term has to be a value to prevent non-termination from getting in. So the answer is yes, with the caveat that sometimes there's also a value restriction. OK, if that didn't make sense, it was technical, don't worry about it. I was going to skip the slide anyway. So I don't mean to, I hope that doesn't sound condescending. I just, I can only get so much into dependent type theory in 45 minutes or whatever. OK, so at the beginning, my whole motivation was I wanted to do extrinsic termination. And you might ask the question, well, can you? And the answer is yes. So imagine I write nth prime in the programmatic fragment. Maybe I've come up with a very complicated algorithm for generating primes. And then I want to prove after the fact that it terminates. I can do that, and here would be the type that does it. This says, this type is a little bit hard to read, but I think not that hard. So what np-total does is it's a logical function, so it's guaranteed to terminate for all inputs n. And for any n, it returns a pair of a natural number and a proof that that natural number is equal to the result of nth prime. So since it's logical, it's always guaranteed to terminate and provide this pair. And this pair is a witness of nth prime's terminations. It's a witness that nth prime produces this value. And therefore, by meta reasoning, np-total is a proof that nth prime always terminates. So the answer to the meta question, can I prove termination extrinsically in zombie, is yes, you can. OK. So that's all I'm going to say about the two fragments. And sorry, question? Yes.
Because you can prove externally that you have termination in programmatic fragment, can you take a type that's added into the programmatic fragment while you're in the logical fragment?
So the answer to that is we don't have explicit support for that, but I think it's built in because np-total's computational behavior is taking in an n and producing the witness of the termination of nth prime, and that witness is the result of nth prime. So np-total is exactly a logical version of nth prime plus a proof part, which you could write a wrapper function that discards the proof part, and then you would have a logical version of nth prime. So I don't think we need explicit support for that. I think it just happens naturally.
And what's kind of funny about that is that np-total is effectively an intrinsic version of nth prime, then?
Yeah, yeah, that's right. I mean, it carries the proof of termination right with it. So sure, yes, in a certain sense, definitely. OK, so I'm already running over time. I'm gonna go quicker, more quickly. But I want to mention that, as was pointed out at the beginning, I'm not the first person to think about this stuff. So let me give you a quick rundown of other approaches to non-termination in type theory. In fact, those of you who are familiar with dependent type theory have been sitting on your hands being like, but what about? And OK, so let me acknowledge the other work. So the most popular way to do non-termination in dependent type theory is this thing called coinduction, right? So if you don't know what that is, take my word for it. It's a thing that exists in Coq and Agda. We have this thing called the partiality monad, which makes it really easy in Coq and Agda to model infinite data, which seems to give lie to my claim that you can't do non-terminating things in Coq and Agda. So it's true that the partiality monad allows you to model infinite data and certain kinds of computation over that infinite data, but you're really restricted in the sorts of computations you can write. So in general, you can only use coinduction to write computations that are over this infinite data, and you must prove that those computations are what's called productive, which means they're guaranteed to only take off sort of a finite chunk of your input and then produce a result before going on to the next piece of the input. So what this is really bad for is the use case that I started with, which is I just don't want to reason about termination for a while, right? If my model is Coq's model, then whenever I define a function, I have to either prove that it's an inductive function, that is, that it terminates, or that it's a co-inductive function, that is, that it's productive. And there's no option to just put off reasoning about termination or not reason about termination at all. What's worse, what I really want to do is start by ignoring termination behavior and then maybe come back later and reason about termination. And coinduction is really bad for that, because when you define a function coinductively, I use a whole different set of definitional tools and reasoning principles. And so it's not trivial at all to move that function back into the inductive fragment. It's basically totally rewriting the function. Whereas in in zombie, the two fragments are much closer together. Okay, so that's why I think Coinduction doesn't quite solve the problem that I set up at the beginning. Also, other authors, and I'm just going to go real quickly through this, have considered terminating sublanguages. The work in these other stuff is really cool. Yes.
You can take more time if you want. You don't have to go super fast.
Thanks, but I really hate it when I come to Boston Haskell and I don't leave until 10, so I'm going to try not to be that guy. Sorry. Well, actually, it is exactly you, Ed. I don't hate it that much, but I want to end by like 9:30 or so. So other people have considered terminating sublanguages. So also I speak too quickly anyway. It's just a problem, as you've noticed. Or and F star are two approaches that do exactly the thing that was suggested, which is that I should have separate kinds, maybe set and prop, that distinguish the terminating and non-terminating fragments. That's a pretty cool idea. I don't think it gives you the flexibility that we have to explicitly manipulate termination, like in the SAT solver example. Also, this has only been demonstrated in languages which aren't fully dependent. So both OR and F star only allow types to talk about values, not talk about general programs. So I think that's a big win for our approach. Other authors have gone farther and completely separated the programmatic and logical parts into separate languages. And what you have then is basically a programming language and a proof logic that are sort of bolted together in one system. And I find that unsatisfying because it doesn't do the thing that I wanted, which was sort of a clean way to go back and forth between these fragments. I want them to be really one language and only sometimes make you worry about whether you know about termination. Although the work by both these groups of people is super cool. I don't mean to suggest that it's not super cool. Okay, so that's what I'm going to say about termination. I want to move on to the other problem, which is equality reasoning, and this section is a little bit shorter. Okay, so what do I mean by equality reasoning? Well, I'm going to do an example in Agda, and this one, it's going to be a little bit, I got a little bit more code in this example, so hopefully you'll bear with me. At the top here, I've written a data type that's a really standard Agda data type. It's what's called length indexed vectors. So these are lists. You see I've got nil and cons constructors with one caveat, which is that their type, in addition to recording the type of stuff in the list, it records how long the list is. So you can also do this in Haskell. It's just a big pain. So that's length index vectors. So you can see like the type of nil, right? It's not just vec A, it's vec A0 because nil is a 0-element list. And the type of cons, the result type on the end there is vec A 1 plus n because it's one longer than whatever the input vector was. Okay, so these are length index vectors. And we can write, so length index vectors are really cool because you can write things like, you can give more expressive types to functions like applications. So here's the type of application for length index vectors. And the really cool thing about this is the return type, which says, oh, by the way, the return vector has length n plus m, where n and m are the lengths of the input lists. So now the type of app verifies that I didn't do something stupid like only return the first list. I'm guaranteed to get out a list that has the right length. Okay, so that's dependent types 101. So then you might ask a natural question, which is, can you prove that vector is associative? Can I prove that if I've got three vectors and I'm sticking them together, can I prove that it doesn't matter which order I do the sticking together in, whether I stick the last two together and stick the first one on the front, or stick the first two together and stick the last one on the back, right? And this is a trick question. So the answer is not only can you not prove this, you cannot even state this theorem in Agda and Coq. Okay, so the type of this theorem doesn't type check, and the reason is the equality at the end there. So the two vectors in the equality at the end, they have subtly different types. One of them has the first type here, vec A n plus m plus k. And the other one is the second type, vec A n plus m plus k. And you're saying to yourself, well, okay, but I know those are the same things, right? I know addition is associative, and that's great. You know it, but the type checker of Coq and Agda does not know it without more help. So in Coq and Agda, when you write down an equality, the two sides of the equality have to have the same type, and therefore just this type is rejected because it's not the case here that those two sides have the same type. Okay, so not only can you not prove this in Coq and Agda, you cannot state it. Of course, that's unsatisfactory, so what do we do about it? Well, here's the solution, the idiomatic solution in Agda. So first I observed that I was going to need to know that plus is associative. So I proved that as a theorem in the language, okay, plus assoc, that says plus is associative. And then I define this function, and conv is a bit of a funny function. What it says is if I've got a proof that A equals B, and I've got something whose type is f applied to A, then I've also got something whose type is f applied to b, because a and b are the same things. So this is going to work really good for the two vectors who were applied to the n plus m plus k, right? Because I'm going to know that those two additions are equal to each other. So, so I can use con to convert the types. So then the theorem I actually end up proving looks like this. And it's way uglier, right? So what I've done is I've added a conv onto the front of the second vector. And this says, OK, I know this vector has a type that doesn't quite match the first vector, but using this conv theorem, I can turn that type into a type that does match the first vector. And so now this type checks. But it's really unsatisfying. So operationally, conv should not do anything. Conv is only messing with the types of terms, right? So this is morally the same theorem that I had before, but it sure doesn't look like it, right? I've added this whole conv. I'm applying a function now to that second vector. And it does, so this is a really unsatisfying version of my original theorem, I think.
Swap the argument between the type of conv and the use at the bottom, or am I really?
It's totally plausible. Let's find out. So vec A is the f, right? So OK, another funny thing about coq and Agda, curly brackets means I'm not going to write it in the application. It's going to be inferred for me, OK? So those arguments are not going to appear in the application, OK? I should have said that way earlier, and I apologize. So vec A here is the f, because remember, vec A is a type that's waiting on a number, right? It's vec A0 is a type, but vec A itself is not a type. So this thing has type nat arrow type, basically. And then this guy is a proof that you know, plus is associative. For n, m, and k, I'm not going to try to say it again, but you can do the parentheses either way, right? So that's this a equals b proof. And so then I go from a vec A with the addition one way to a vec A with the addition the other way. And so now this whole term has the same type as this term, because I've swapped the way the addition works. OK, so you can do this, but it's super unsatisfying because the theorem no longer looks quite like the theorem I wanted to prove. OK, and that's a real bummer. OK, so two problems. We can't cleanly state equalities that are between things that have different types. And when we fix it, we no longer end up with the theorem that we wanted to prove. OK, so what are we going to do about it in Zombie? Zombie's equality is heterogeneous, which means it's natively such that the things on both sides of the equality don't have to have the same type. Okay, so here's an example of that. Here I've got a decision procedure for vector equality, and it takes in a vector of length a and a vector of length n and a vector of length m, and it tries to produce a proof that they're equal. But of course, the type of that proof on the end, the two things on the left and right hand side of the equality don't have the same type. One of them is length n and one of them is length m. And that's OK. You can just state this equality in Zombie. It's allowed now. Okay? Before, this would have been rejected because the two sides had to have the same type. But in Zombie, it's not rejected. It's allowed. OK. In Zombie, equality has a very operational flavor, so we've already talked about this. Two expressions are going to be equal just when they reduce to the same thing. So to type check REFL, right, we just reduce both sides of this equality, and we find out they're both 3, so it's allowed. I've talked already about some type annotations, and I'm going to talk about more. And so I want to emphasize again that that we erase all type information from terms before we compare for equality, and this includes uses of things like this con function. Okay, that's messing with type, so it's going to get erased. And so that's going to be a big win. If you've programmed with dependent types, you would know that those types of things can get in the way of equalities because you've got a conv on one side and not on the other, and they're not going to get in the way anymore because we're going to erase them. So these are big wins. So let's do more examples. In Zombie, many conversions can be completely unmarked because of our type inference. So this is a sort of boring function. It's the identity function for the last argument, right, for the vector. But its type does something funny. It changes the type of the vector. And what's going on here is that the Zombie type inference can see that I've got a proof that n equals k, so v has both types. It has both a vector of length n and a vector of length k as its type. And as I said before, equality is both heterogeneous and operational. So this equality type checks. So this is, I've got v, who's a vector of length n, and a proof that n equals k. So on the left-hand side, I've got a vector of length n. On the right-hand side, I've got a vector of length k. And I'm allowed to write that down because Zombie's equality is heterogeneous. And also, Zombie's equality is operational. So the proof of this is real easy because len swap is just the identity function. And so it just computes both sides. It finds out that they're both v, and the equality goes through. Yes?
Sorry. That vector from the len swap to v.
Yeah.
So magic is occurring here, right?
Well, you say magic because you're used to Coq, where I would have had to write match p with, and then use that equality explicitly. But I would argue it's not very magic at all. Those two things have the same type.
When it's typechecking, then this.
Yeah, you're right. Magic is super recurring. I'm gonna own up to the magic on 2 slides. Okay. So there's a fancy inference algorithm going on here that I'll own up to in a minute. But my hope is that this looks really natural, right? Like there's nothing surprising on this slide from a sort of operational perspective. Okay, so now here's where I own up. The zombie inference algorithm implements this thing called congruence closure, which is a thing from rewriting, I guess. And I don't mean I guess. It is. Okay, so here's an example of that. So there's this constructor called smartrefl, which when you use it instead of refl, it's going to try to do like even more hardcore inference with the equalities that are available in the context. So here's a really interesting function. It's a proof that n plus 0 equals n. And it turns out that because of the way a plus is implemented for natural numbers, n plus 0 does not just reduce to n. They're not the same thing according to my notion of terms that reduce to each other. When you try to reduce n plus 0, you get stuck because you don't know what n is. n plus is implemented by pattern matching on the first argument. So to prove that this equality is actually true, I'm going to have to unfold that pattern match, and I'm going to have to check. And then in the case where n is 0, the equality is obviously true, because 0 plus 0 is 0. But in the case where the first natural number is the successor of another natural number, it's not obvious anymore. The thing that I have to prove in that case is that the successor of k plus 0 is equal to the successor of k. Well, luckily, by a recursive call, I'm going to know that k plus 0 is equal to k, because that's smaller than my original input. So here what I do is I let bind that recursive result. So n plus 0 has this type, k plus 0 equals k. And then I let bound it, but I didn't even give it a name, because I don't have to use it explicitly. This very fancy congruence closure algorithm was going to find for me that it needs to use this equality as a congruence here where suck is applied. Okay, so this is really cool. I don't want to take any. So first of all, let me say equalities get erased in core terms. So like this let binding even will get erased. It's not going to get in the way of computation. That means that it doesn't add any runtime cost, and also it doesn't get in the way of equalities. And secondly, I didn't do any of this. So this is like a major contribution of Wilhelm Schoberg's thesis, and if it sounds cool, you should read both his thesis and his Popple 2015 paper. But it is implemented in this zombie research language. And it's really cool. So I wanna tie all together by coming back to my original example, except I'm going to cheat a little bit. So the question is, can we prove that vector append is associative? And the answer is, in zombie, yes. First of all, the type just type checks because we allow heterogeneous equality. And then also, the proof is not too bad to write. But I'm going to assert that and not demonstrate it, because here I'm showing the core erase term instead of the high-level term that you would write in zombie. And the reason is we need a few more let bindings in this one, like in the previous example where we had this let binding and recursive call. We need a couple more of those in this one to help the congruence closure algorithm, and they don't quite fit on the slide. But it's not that bad. And they all get erased, so this is the core term we end up with, the theta term that I was talking about earlier. Yes?
If you don't write the let underscore whatever terms, how bad are the error messages?
The error messages are universally abysmal because it's a research language. It doesn't matter whether you write what you write, okay? They're real bad. So, yes. In this case, you would get an error message that said, I can't prove these two things are equal. So actually, maybe it's not that bad.
At least unlike GHC, error messages fit on the script.
Yeah, so it could be worse, but it's not. We've put no effort into optimizing the error messages. Again, this is research territory. This is not. Do not try to write zombie programs. Okay. Right. So the reason I've shown the core term here is because we have to add some of those lets with lemmas. But the congruence closure can use those, and you do end up just writing REFL, and then they all get erased. So you get this core term, which is beautiful in my opinion. OK. So that was sort of a whirlwind tour. I don't have a ton of time. In fact, I'm really running quite short on time. So hopefully the perspective you got is that equality is pretty cool in Zombie. It is. OK, so what about other approaches to equality-independent type theories? Most popular approach is John Major equality. Here's this inventor staring at John Major, sort of. The spoiler, since I'm going quickly on John Major equality, is that it allows you to state these heterogeneous equalities, but you can't use them. And so it doesn't really work at all. Why is it called John Major equality? It's a joke about British politics. I don't know, Google it. OK, so observational type theory, somebody was asking about epigram earlier, is a really promising approach. I would say the major difference between observational type theory and our approach is that observational type theory is very focused on types. So what they do is they add axioms to make more equalities check, whereas our approach is just operational. Not only is it not focused on types, it gets rid of as many types as it possibly can, right? So the original problem was that we can't prove as many equalities as we want. OTT fixes that by adding axioms that allow you to prove more of those and then giving those axioms runtime behavior. Zombie fixes that by getting rid of as much type information as possible, so now those equalities do go through. So two different approaches. And I think actually OTT is a super promising approach. I'm not saying anything bad about it, but epigram continues to not materialize, so I have never played with it. OK, lastly, there's this language called Guru, developed by Aaron Stump, and Guru's equality looks a lot like Zombie's equality. It actually goes even further in caring less about types. You can write equalities between terms that don't even type check. That turns out to be super inconvenient, which is why you can't do that in Zombie. But really, Zombie equality should be called Trellis equality because there was this, I mentioned there was this collaborative Trellis project, and this is definitely one of the things that came out of that collaboration with Aaron. So I want to own up to that. OK, metatheory, it's hard. OK, so here's the highlights. We've proved nothing about Zombie. That's not true. Wilhelm's thesis proves things about a large fragment of Zombie. The most work has been done instead on proving things about Zombie's core language, which is fine because Zombie's core language is the thing that gets run anyway, so there's no real reason to do proofs about the server's language itself. We have not proved things about the whole Zombie core language. Instead, in my thesis, I proved things about PCC theta, which is kind of like almost a Zombie core language. I'll confess to what it's missing in a second. What's cool is that we do have a complete proof that that core language is type safe and that its logical fragment is normalizing, which, if you know anything about dependent type theory, is super hard to prove. And it's doubly hard in the setting where we've got this weird equality and this non-termination. Sorry, by normalizing, I mean everything in the logical fragment does terminate. We can prove that.
Sorry. Do you have the type checker? I mean, is the type checker part of that specification?
I don't understand the question.
So somewhere in the type checker, you use this congruence closure.
Yeah, so what happens is the congruence closure gets, we elaborate the congruence closure into a more explicit language, which is basically PCC theta derivations. Those are the things that get type checked, and then we erase away the extra annotations to get PCC theta terms. So yes. If you're curious about the details of this proof, it's explained in some detail in our Pobble 2014 paper, and also we even mechanized substantial parts of it in Coq, so we can really believe these results.
Sorry, so you went through the results really quickly. Did you say the logical fragment actually is a logic?
Yes, it is absolutely, for PCC theta, which is not all of theta, it is absolutely a logic. That's what we proved. So what is it missing? What PCC theta is missing is primarily a universe hierarchy and data types. Okay, those two features are not in PCC theta. Data types I don't think are tricky. They just add a lot of notational clutter to your type system when you're doing proofs. Universe hierarchy is like impossible. So there's a whole chapter in my thesis about like where everything goes wrong, and that's one of the primary things. So if I had more time, which I guess I'm being told I do, but I'm not going to take it, I would go into detail about PCC theta's metatheory. I'm happy to talk about it after. It's cool and challenging. Do I want to say anything in particular from these slides? Okay, the particular novelty that we came up with is using step index logical relations in a normalization proof. Now, if you know things about type theory, that means something, and if not, okay. But wait, there's more, so let me acknowledge the, where you can, sorry, let me point again to where you can read more about this if you're curious. You can read our Popple paper from 2014, which talks about the metatheory of zombie. That's elaborated in my thesis. You can read Wilhelm and Stephanie's Popple 2015 paper, which talks about the congruence closure type checking, and that's extended in Wilhelm's thesis. And I should say that's not the only contribution of Wilhelm's thesis, but it is part of it. And lastly, if you want to try out Zombie, you can get it on GitHub, but don't. It's super experimental. This is not like you're going to download Agda and play with it, right? This exists only to the extent it needed to write these theses. It's really a research language, not in the way that Coq is. There's no tooling. That's just a lot of man hours that we didn't have. But you can do it if you're especially intrepid.
Do you have any way to step through your proofs, or do you just like write them? And
Which proofs are those?
Just any proofs that you write.
In Zombie? Yeah, there's no tactic language. There's no proof general. There's no holes like you would have in Agda. It's like you're really doing God's work when you write Zombie programs. You're writing out the whole terms, and there's no getting around it, except for the nice congruence closure. Yeah. So again, the point of this talk is to introduce these research ideas to demonstrate that we've shown that. They do play nicely at a theoretic level, and that I think they're plausible solutions to some of the problems with existing independently typed languages. Not to say, okay, we've implemented them in a real tool. That's a lot of work that we have not done. But maybe we could do in the future if people like the ideas. Yeah, so that's everything I have. Thanks a bunch for listening. I want to say one other thing, which is that I work at Draper Labs in Boston, and if you are a Haskell programmer, we would love to talk to you. We do all kinds of fun stuff, not type theory, but we do like static analysis stuff in Haskell. So it's PLE stuff. It's fun stuff. We would especially love to talk to like students who want to do internships and that kind of thing. We need more people who are excited about Haskell in general. Thanks very much.